some sense, everything in the course up to this point has been leading to this lecture. Okay, we're going to finally find out how, if you drop your robot or agent into some unknown environment and you don't tell it anything about how that environment works, how can it figure out the right thing to do? How can it maximize its reward in that environment? How can it figure out the actions that lead to the most possible future reward without telling it anything in advance about how this environment works? So that's the goal of this class, model-free control. And after we've seen this class, in the subsequent lectures, we'll look at how to scale up, how to get to more realistic, large-scale domains. But the core techniques are essentially building on what we saw in the last lecture and bringing those into a control setting now. So roughly the proceedings for today, we'll have a brief introduction. And then what we're going to look at is two different paradigms for doing control, on policy and off policy, which will understand the distinction between those. Essentially, on policy means learning sort of on the job, whilst you're following the behavior that you're learning about, and off policy means learning whilst following someone else's behavior. And so we'll start with on policy, which is a simpler case. And again, just like last lecture, we're going to follow the format of starting with Monte Carlo control before we move on to temporal difference learning to get more efficient, lower variance techniques. So how are we going to do that? Well, last lecture, we basically built up the toolkit that we're going to need. Last lecture, we saw how to do model-free prediction, how to evaluate a given policy. If you drop your robot into a given MDP and you ask it how much reward will it get if it follows a particular behavior, last time we saw how to do that using Monte Carlo evaluation and temporal difference learning. And that just helped us to estimate the value function of some unknown MDP. And now that basic toolkit is what we're going to use to now do control methods, where we want to not just estimate the value function, but actually optimize it, find V star, find Q star, find the best possible behavior, find the most reward you can extract from this MDP. But we're going to use the same tools, and we're just going to iterate them and essentially use what we had before kind of as an inner loop for getting to the best possible behavior. So just to get you back in the flavor, I know we've had a week off, reading week, so I think it's helpful just to get a reminder of why this is interesting. Why should we care? Why should we care about this particular flavor? Why this problem of unknown MDP reinforcement learning? And the answer is that in most interesting problems, and I put up just a few interesting problems here that all fall under this umbrella. So controlling an elevator, getting some car to park itself, trying to automatically steer some ship, or control a bioreactor, or navigate a helicopter, or do the logistics for an aeroplane, or play Robocup soccer, or control a bot in Quake, or manage a financial portfolio, or learn how to fold proteins, or figure out how to make a robot walk by itself, or to play a complicated game. All of these problems have MDPs. There are MDP descriptions of these problems. In each case, there's some complicated environment in which this problem can be described, where there are some underlying dynamics in some environment that has some state that tells you how it's going to move around in the state. But either that thing is unknown to us, we don't know what that environment is, and so we have to resort to model-free control to figure out how to do this. Or the MDP might be known, but it just might be so complicated that it's actually too big to use except to sample it. And if you can only sample it, you're essentially back to the same case as model-free control, where you really, the only way you can access this model is by just trying things, trial and error, and see what happens. Because you can never do even one step of integrating over some vastly complicated model. It might be too expensive. The real world's an example where the underlying dynamics of the real world are extremely complicated. Even if we knew them, you wouldn't really want to work at the atomic level and integrate over the dynamics of every atom moving around. You would just take samples, see what happens, and work with that. So model-free control helps us to solve problems like these. So that's why this lecture is interesting, I hope. Okay, so we're going to look at this basic dichotomy between on-policy learning and off-policy learning. So let's just understand what that means now. So on-policy learning, I like to call it learning on the job. So it's like you've got some policy, you follow that policy, and while you're following that policy, you learn about it. So you basically it's actually a sampling experience by sampling actions from some policy pi, and at the same time you're trying to evaluate that same policy. That's what we mean by on-policy learning, that the actions that you take determine the policy that you're trying to evaluate. But that's not the only choice. We can also do off-policy learning, which you can kind of think of as looking over someone's shoulder. So you might have some robot which is watching some other robot walk around, and it's trying to figure out the optimal behavior by just observing some other robot, or maybe even a human, behave. So maybe a human gives some example demonstrations, maybe some teleoperated arm, and the human says, this is how you should move this arm around. And now, just from the trajectories that have been sampled from the human behavior, we could actually do off-policy learning, and we could learn to evaluate. The robot could start to learn for itself, well, what would happen if I did something else? Maybe there's some better behavior, and the robot can learn about that better behavior from samples of experience drawn from, say, the human behavior. You don't have to learn about the behavior that you sample. You can learn about other behavior. That's called off-policy learning. Okay, so we'll start with a simpler case on policy learning. And the main idea that we're going to use throughout this course is the same idea that we saw a couple of lectures ago when we were doing dynamic programming. And it's the basic framework of generalized policy iteration. So just a quick refresher slide. So the main idea in policy iteration is to alternate between two different processes, where first of all we evaluate a policy, and then we improve that policy. And we have this iterative process, which I kind of sketched up on this diagram here, where you start with some value function and some policy, and every step, every time you go up, you basically evaluate your current policy to get you a new value function, and every time you go down, you act, say, greedily with respect to that value function. I should just say greedy, actually. And so this alternating process we saw when we were doing dynamic programming actually does converge on the optimal policy and the optimal value function. And it's just this cycle that can go round and round and round. And the question is, well, what can we slot in for these two processes? And what we're going to do today is we're going to vary the choices of what slots into these two pieces here, so to enable us to do model-free control, rather than in dynamic programming where everything was using full knowledge of the MDP model. So far we've only seen in the dynamic programming examples of these where our up arrows were some way to evaluate the policy, and we saw things like iterative policy evaluation, and the down arrows were things like greedy policy improvement. And now we're going to vary those two components and try other choices. So let's make a first try. Okay, let's say we want to do the simplest case. Let's start with Monte Carlo learning. So we're doing basically Monte Carlo control. That's this section. We're in that chapter of the lectures. And so we're going to start with Monte Carlo control. Later we'll move on to TD control. Now if we're doing Monte Carlo control, is it possible to just slip that in? Can we just swap in Monte Carlo policy evaluation instead of our dynamic programming? That would be a way to evaluate the policy. So remember, Monte Carlo evaluation is just, you just execute some trajectories and take the mean. And that's your value of your value function. So what about doing that as our process for estimating the value of the policy? What would happen if we just ran some trajectories, used those trajectories to estimate V, and then applied greedy policy improvement? Would that work? Any thoughts? Any problems with this idea? Do people understand what the suggestion is? That we can take this general policy iteration framework and plug in a model-free step for policy evaluation to just run some trajectories in the unknown environment, see how well we do, use that to estimate the value of the policy, and then iterate by improving our policy, evaluate the new policy by running some more trajectories, evaluate our new policy, act greedily with respect to that, run some more trajectories, etc. And according to our knowledge of generalized policy iteration, this has to converge on the optimal policy. So what's wrong? Can anyone think? There's actually two problems with this. Okay, good.
So if when you're running your trajectories, you follow your policy, then you're not going to explore very well.
Okay, great. So that's one of the two problems. We'll actually come to that one second. So, but the point was, which is correct, is that there's an exploration issue, which is that if you act greedily all the time, you don't guarantee that the trajectories that you're following explore the entire state space. And so it might be that there's parts of the state space which are really interesting and actually have better potential that you just never see. Okay, there's one more problem with this. Any thoughts? So that's actually the problem with the second step. Any problems with this first step, with evaluating V in this way? Yeah?
You need to run a whole load of trials to get a good measure of what the best policy would be at any given step.
Okay, so the point was that maybe it's slow to do this, that it might be, you might need a lot of episodes to actually make this work. That's true, and we'll improve on that by using temporal difference learning later. But let me move on. So the issue is that we're trying to be model-free, actually. We want to be model-free, But how can you be model free when you're using the value function v? If you use the state value function and you only have the state value function, and you want to act greedily with respect to your state value function, you still need a model of the MDP to figure out how to act greedily with respect to that value function. You only know the value of each state. And so if I'm in some state and I want to know, well, which action is best, I have to imagine what would happen for each possible action. I have to roll forward the dynamics one step to look at the value function of my successor state. We don't know those dynamics. We're trying to be model free. Okay? So if you work with the state value function v, you always need a model in order to do your policy improvement, because you need to have some one step of look ahead to get to your next state. So the alternative is to use Q. The alternative is to use action value functions. Action value functions enable us to do control in a model-free setting. And the reason is that we can do policy improvement in an entirely model-free way. Like if we have Q and we want to do greedy policy improvement, all we need to do is maximize over our Q values. So we've got the Q values. The Q values tells us from each state how good is it to take each different action. Now if we want to make a better policy, what do? Well, we just pick the action that maximizes our Q values. That's the best action. It's immediate. You don't need a model to roll anything forward. It's already there in the structure that we've created. So by caching the values of our actions, we would kind of reduce the burden of what we require from our model. We don't need to look at the model anymore. We don't need to roll it forward. Is that clear? Okay. So let's drop that in. So what would that look like now? So the proposal then is that we have now an algorithm which looks like this, where we start with a Q value function now, an action value function, and some policy. And every step we're going to do a Monte Carlo policy evaluation, run a bunch of episodes. At the end of those, we've got some estimate of our policy of Q pi. So we run a bunch of episodes. We take the mean from each state action pair. We look at the mean return to estimate QSA. And that tells us how good that particular state action pair is, taking that action from that state. What was the mean return that you got? Do that for all states and actions. That gives us a new value function. We then act greedily with respect to our Q. That's immediate. We just take this argmax over our Q values. That gives us a new policy. We run that policy for a bunch of more episodes, take the mean of all our state action pairs again, and iterate. And again, this results in Q star and pi star, or does it? And the issue has already been raised by someone in the audience, which is we still have one issue, which is that we're acting greedily as our policy improvement step. And if you act greedily, you can actually get stuck. You can actually not see the states which you need in order to get a correct estimate of the value function. So we're basically estimating the value of all state action pairs by trial and error, by running episodes. But if we don't see certain states and actions, then we won't evaluate them correctly and we won't select them because we haven't seen how good they are. So that's the distinction. Now that we're running things, we're not doing these full sweeps that we were seeing in dynamic programming. We're running things by actually interacting with the environment. So we need to make sure that we continue to see everything. So here's an example to make that a bit clearer. Okay. So this is something from the academic world where you can imagine there's some situation in life where you've got two doors and you're trying to pick the best door. So in this cartoon, one of them behind that door is tenure, or one of them has tenure, and one of them is flipping burgers at McDonald's. So now we have to basically figure out by trial and error which door to go through. So let's say you get repeated trials, and let's say the outcome of these doors is actually stochastic. Okay, so you're just going to get some immediate reward. This is called a bandit problem. We'll see more examples of this in a subsequent lecture when we focus really on exploration. But it's a bandit problem. You've got two choices, door 1 or door 2. So what happens now? If you open the left door and you see a reward of 0, okay? So you get this reward of 0 for going through the left door. So now think, okay, 0 wasn't so great, maybe I'll try the right door. So you open the right door and you get a reward of +1. So if you're acting greedily, there's only one logical thing to do, which is to open the right door again. Let's say it gets a reward of +3. So now your mean, after these steps, you've seen 1 + 1 and 1 + 3. So your Monte Carlo estimate of the value of that door is now +2, the mean of those two episodes that you've seen. So +2 is clearly better than 0. So if you're acting greedily, you would pick it again. Maybe you get a reward of +2 again. And now you've got a mean of 2. So you'll open it again. And then maybe your mean is just going to fluctuate a little bit around 2. Let's say you always get a reward between, say, 1 and 3. You'll keep on opening this door forever. And the problem is that actually we don't really know what the value of this door is. We've only tried it once. And so you need to carry on exploring everything to make sure that you understand the true value of all of your options. If you stop exploring certain actions, you can end up making incorrect decisions, getting stuck in some local incorrect optimum. Your beliefs can be incorrect, and you need to carry on exploring to make sure that you really understand the values correctly. Okay, so do people see how you can get stuck in this situation and just keep on misevaluating? So how do we do that? How do we make sure that we carry on? Well, there's going to be a whole lecture on this, but we're going to start with the simplest possible way to guarantee that you continue to visit all states and all actions infinitely often. And so this is the simplest idea for ensuring continual exploration. It's actually surprisingly hard to do better than this simple idea, although there are lots of much more sophisticated algorithms. And the simplest idea is what's called epsilon greedy exploration. And it's very simple. All it says is that you flip a coin. With probability epsilon, you choose a random action, completely random, a uniform random action. With probability 1 minus epsilon, you choose the greedy action. Okay? So you flip a coin. If it comes up heads, you act completely randomly to make sure you see everything. If it comes up tails, you choose the best thing that you know so far. You take your argmax over your Q values. So it's just like our greedy policy improvement, but we've softened it a little bit to make sure that with some small probability, you try all the other actions. So this might seem naive, but it has some nice properties. It guarantees that you continue to explore everything, and it guarantees that you actually improve your policy as well, as we'll see shortly. So this is just a fancy way of saying precisely that. This is saying the probability is if you flip the coin. So this epsilon over m is the probability of what happens if it comes up tails and you explore, and this 1 minus epsilon is the probability of actually if it comes up heads, then you pick the greedy thing. But you might also pick the greedy action just by random as well if this tail thing comes up, which is why I have a bit more probability mass on this one. But the idea is very simple. You just either take the best action or you explore at random. Okay, so one of the reasons that epsilon greedy is a nice idea is that it actually guarantees that we get a step of policy improvement. So remember, for this generalized policy iteration idea, we want to alternate between steps of improving our policy and steps of evaluating our policy. And so what we can see is that epsilon greedy actually is a policy improvement. Like you start off with one epsilon greedy policy, and now the question is if you evaluate that policy, so you start off with pi, that's your previous epsilon greedy policy. If you evaluate that to get you v pi, the question is, can we be sure that by taking epsilon greedy step, like by acting epsilon greedily with respect to v pi, can we be sure that we've really made a better policy? And the answer is yes. So the simple proof here, which basically says that if you look at, so we're just going to do the same idea we saw in the dynamic programming lecture, where we're just going to prove this over one step, and then we're going to argue that that whole thing telescopes by unrolling it using the Bellman equation. So over one step, we can see that the value of our previous policy, of our original epsilon greedy policy, if we take one step of our new policy, so we want to show that this thing here, taking one step of our new policy, is basically better than our original policy, than the value of our original policy. So this is just saying, well, this is just an expectation. So this is our epsilon greedy policy. And we're going to say for one step, there's some probability that we're going to take each action, multiplied by the value of that action. This is just unrolling the expectation. And we can split that into the probability of taking the greedy action plus the probability of taking or every action. So this is what happens if you choose to explore, and this is what happens if you choose to act greedily. And now what we can say is that, well, this thing of where you choose to act greedily, if you choose the max of all your Q values has to be at least as good as any weighted sum of all of your actions. Right? The max is better than any weighted sum of your actions, of your Q values. So we're going to choose one particular weighting that sums to 1 here. And we're just going to say that the max has to be better than that weighted sum of your Q values. And now you can just collect terms together, and we see that we've got 1 minus epsilon on 1 minus epsilon. So this term over here now just cancels with this term over here, and you're just left with an expectation over your Q values, which is your original value function. Okay, you can look at this afterwards, but the main thing I want you to take away is this idea that epsilon greedy, very simple idea, but it really does guarantee that you're making progress. So you really do make progress. You start off with some epsilon greedy policy, you evaluate it, you make a new epsilon greedy policy, and it's definitely better than what you started with, or at least as good as what you started with. Okay, and then for the final, to telescope it, refer back to the dynamic programming lecture that explained how this telescoping argument works. It's the same idea. Okay, so that's the one slide of math. Go on, question.
Well, this proof you've just showed us doesn't really tell us anything about the rate of being exploration, really. Because I think if you did like completely greedy policy, then that would actually, prove that's better than anything, but you're not taking into account you actually need to explore the environment more.
So I'm not sure I understand the question. So is the question, can we say anything about how frequently you need to, like what, how epsilon affects?
Is it telling us anything about, in our real problem, when we execute our real problem, how much we should be exploring?
No, this doesn't really in itself tell us anything about how rapidly we should be exploring. So, but in general, we'll see a little bit about that in a second, that you need to choose a schedule for your epsilon, and you need to make sure that that decays to 0 roughly, but we'll see. So let's see how to plug that in now. So we've got two ideas now. We started with this generalized policy iteration framework, and we've changed each of these steps now. We have these two processes. So for the policy evaluation, we're now plugging in Monte Carlo as our way to evaluate our policies using Q, using the action values. So we've got this one process here where we just run some episodes using our current policy. We estimate the value of all states, all actions from all states, just from what we've seen. So for every state action pair, we look at the mean return we've seen. That's our evaluation procedure. As someone's pointed out, that might be a little bit inefficient, and we'll see how to improve that shortly. But now, we've also changed our policy improvement procedure to use this epsilon greedy policy improvement, where we basically have this softening of the greedy idea. So every time we go down, we're not getting to the completely greedy policy, we've got a little bit of exploration left. And so the policy is always stochastic along here now, and that stochasticity in the policy ensures that we, at some rate at least, explore everything in the environment. Now, as pointed out by the question there, the rate at which you actually see, it might be very, very slow still. There might be some states that are way off down some strange trajectory, and you have to explore and explore again and explore again to be able to even see those states. So this doesn't actually give you very strong guarantees of how long it takes to explore all of those states. It just says asymptotically, at least, this thing now really will find the optimal policy at the end. I should say Q star. This should all be Q rather than V. Okay, so let's try and make this a little bit more efficient. So the first thing to note is, again, we saw in the dynamic programming lecture, that it's not necessary in these kind of policy iteration frameworks, it's not necessary to go all the way to the top of this line every time. It's not necessary to fully evaluate your policy. Sometimes you can just spend a few steps to evaluate your policy, and you've already got enough information there to guide you to a much better policy without wasting many, many more iterations on gathering more information. So what would that look like in the context of Monte Carlo? Well, let's take it to its extreme and say, why not do this every single episode? So we're going to run one episode, going to make the robot do one episode, collect all the steps along that episode, update the Q values just for those steps, so we basically get one new return. And so for every state and action that we've taken along that return, we're going to update the mean value just of those visited states and tried actions along that episode. So one episode, one sequence of updates to our returns, and then improve our policy straight away. Why wait? Why wait to get more episodes of information when you can already improve the policy? So the idea is, always to act greedily with respect to the freshest, most recent estimate of the value function. Like if after one episode you can already update the value function to something slightly better, then why continue using your old estimate of the value function to generate behavior? You may as well use your new updated value estimates to continue generating behavior. And so we changed the sort of the time, the rate at which we operate in this diagram becomes more frequent. The frequency increases. We don't go as high up. We just run one episode, and then we immediately improve the policy. One episode, immediately improve the policy. Run one more episode, improve the policy. Is that clear? Okay. So this question's already come up, and it's a natural question, which is, how can we really guarantee that we find the best possible policy? Like what we really desire is pi star. We really want to know the best possible behavior in this environment. So to do that, we have to kind of balance two different things. We need to make sure that we continue exploring to make sure that we don't exclude things which are better, but we also want to make sure that asymptotically that we get to a policy where we're not exploring at all anymore, because we want the best possible policy, and the best possible policy will not include this random behavior. That is extremely unlikely to be optimal. So how do we balance those two factors? And so one idea for balancing those two factors is called this GLEE idea, greedy in the limit with infinite exploration. And the idea of GLEE is basically to come up with any schedule, if you like, for exploration, such that two conditions are met. The first condition is that you continue to explore everything, that you basically make sure that all states and all actions are visited infinitely often. So that's like guaranteeing that you just that you never miss out on anything. That just to make sure that every little part of the state space will be seen, every action from every part of the state space will be tried. So, for example, epsilon greedy has that property that eventually, if you behave randomly and you try all possible actions, then every reachable state in the state space and every action from those reachable states will be tried. Okay. And the second property is that we want to make sure that the policy eventually becomes greedy. And it needs to become greedy because we need this thing to satisfy the Bellman equation. And the Bellman equation is basically, the Bellman optimality equation basically requires a max in there, not just some soft thing. And we want to make sure that eventually we're acting greedily with respect to Q, and we're really taking the max, or the argmax of our Q values, eventually. And so one way to achieve this, by no means the best way, but certainly one simple idea, is to choose an epsilon greedy policy and just decay epsilon slowly towards zero. So for example, if you choose a hyperbolic schedule, so each episode, you basically, on the kth episode, you set your epsilon to say 1 over k, that satisfies these two properties. That you will see everything infinitely often, but asymptotically you become closer and closer to optimal. Closer and closer to the greedy policy. Okay, so that's one way to balance things. So what does that look like in practice? Well, we can make an algorithm now. Let's call this GLEE Monte Carlo control. So this algorithm, basically we start off by sampling episodes. So again, we've just got our robot, we throw it down, we run one episode, that generates a trajectory of states, actions, rewards, that state, action, reward, until we get to some terminal state. We sample that from our current policy, pi. And then for each state and action that I visited, so I got to this state and I picked this particular action, for each of those states and actions, we update our action value. And the way that we do that is just by counting how many times we've seen that state-action pair and doing an incremental update to the mean. So this is just our incremental update to the mean, which says that if we consider that particular state-action pair, this one over here, this state and this action, how many times have I tried that? Well, let's just adjust our previous mean, which was this. We're going to update a little bit in the direction of the return that we just got. And the amount that we have to adjust it to get a correct mean estimate is this 1 over n. Now, what's interesting about this is we're not taking a mean in the way that you think of it's not like a statistical mean over some IID quantity now. that the policy is actually changing over time. We're iterating over our policy, we're improving our policy, but we're basically taking returns from better and better policies into account. So as we improve our policy, we're gathering more and more statistics, our policy starts to get better, and we collect all of those statistics together to get us one overall mean of how good it is. And the GLE property basically ensures that over time, that these statistics that we're collecting really sort of converge on getting the mean return for that these policies sort of get more and more like the greedy policy. And so we basically find out more and more information about the policy that we really care about, that the past kind of gets dominated eventually by these new policies. And so what we're going to do now is we're going to iterate over this whole process. So we're going to sample a kth episode in this way, update our Q values, and then improve our policy. So this was the policy evaluation step. Now the policy improvement step just looks like this, where we can, for example, set epsilon to its new value, 1 over k, and now we're just going to act epsilon greedily with respect to these new Q values. And those Q values are going to be the same everywhere, apart from the states and actions that I just visited. So we only update those Q values along one trajectory, but that's already enough to change the behavior that we actually see there. So in practice, if you're actually writing this, you don't need to explicitly store pi, you just store Q, but when you actually come to select actions, you always just look at the freshest, most recent Q, and you flip a coin and you either pick the maximum Q, or you pick a random action. So this pi is kind of implicit, and all you need to remember is your 1 over k schedule that you're using to determine the bias of this coin that you're using. And this algorithm actually finds the optimal action value function. So this is really, this is our first full solution. This is something which you throw it into any MDP, and you just let loose with this thing, and it will find the right solution. And it's considerably more efficient to run it in this way, where you actually update the Q values every single episode. You update your Q values and then immediately improve your policy, rather than having to generate a whole batch of episodes, thousands of episodes, to just get one evaluation of Q. So this actually works much better in practice. Okay, are people clear about this algorithm? Like the idea? It's a good time to ask questions if you're not, because we're just going to keep on adding to these ideas. Okay, good. I'll take silence to mean comprehension. Okay, question.
And I can't remember if you addressed this in an earlier lecture, but is there any particular idea behind the initialization of the values for Q, or do you do random initialization?
Okay, so the question is, does it matter how you initialize Q? And in terms of the theory, you can start with anything. It will still converge. In practice, of course, it helps to have a good estimate of Q. The closer you are to the optimal Q values, the faster this thing will converge. It's a bootstrapping. Sorry, it's not bootstrapping like with TD, but still, we're basically starting from these Q values, and we're updating incrementally from. Actually, sorry, that's not true with this particular schedule. let me back off that. We'll see that for later versions where we have an incremental update. So for this particular algorithm, it makes no difference because we're just taking the mean, and so the very first time you see a new state action pair, you'll replace any Q value that you started with completely, because n will be 1. You completely replace your old Q value with that return that you saw.
Right.
So for this particular algorithm, it makes absolutely no difference what your initial Q values are. In practice, and in the rest of this lecture, we'll see algorithms where you don't have this perfect mean, but instead you have some non-stationary estimator that has something like a constant alpha here. And for those algorithms, it matters much more what Q values start with, because you're incrementally moving on from that initial start value. And then your start value, the closer you are to optimal, the better. So, yeah, sorry. Correct myself there. Okay, question. Then I'll move
You
on.
said it's more efficient to update for every episode.
Yes.
But if you do it for many episodes, you have the chance to parallelize the process, so you run a lot of episodes in parallel. With
Okay.
the same value function, whereas
So that's a great
with this
point.
you
So.
have to wait.
So I guess, yeah, I'm just focusing on serial computation for now. There are many possibilities for exploiting parallel computation, and you're right that you would want to that parallel computation introduces constraints on what you can and can't do, and you may want to. It's almost. I think the same is roughly still true with parallel computation, that you still want to use the freshest possible Q values that you can, but with parallel computation, those might necessarily be a little more stale than the very latest episode to come in, because you simply don't have access immediately to all of that parallel computation. Okay, so let's just do a quick example. So we had this Monte Carlo example in a previous lecture. In last lecture, we just looked at evaluation. We basically said, okay, if I send you into a casino and I tell you that you have to stick, basically unless you're always going to ask for a new card unless you're on 19 or 20 or 21, I think was the policy we had before. And then I want to know how much money would you win or lose in that casino. So that's what we looked at before, and we had a particular plot of the value function, and it had a particular shape to it. And now what we're doing is we're actually running this algorithm we saw on the previous slide to generate the optimal value function. So now this is the question you probably really want to know, which is, you know, if I walk into a casino, what policy should I play to get the maximum possible amount of reward? And again, real casinos use slightly different rules, so don't try this. But I'm not responsible if you lose all your money. And so this basically tells you, now we've run our Monte Carlo, we've iterated through several processes where each episode we update our value function a little bit. We actually store Q internally, but just to make the plots easy to look at, we're now basically summing over all of the actions to estimate V star from our Q. So you basically have some Q, that generates some epsilon greedy policy, and then you alternate backwards and forwards by running these episodes just like we saw in the last algorithm. And you end up with a policy which looks something like this, which says that if you don't have an ace in your hand, you should actually have this quite interesting looking policy, is the optimal policy to follow, where depending on what the dealer has here and what cards you've got, you know, it's this threshold somewhere between like 16 and 17, where if you've got 16 or less, it's better to ask for a new card. But there's some situations where a dealer has some kind of quite difficult card to play with, where there's a high probability the dealer will go bust, in which case you should probably just stick anyway and just wait for the dealer to go bust. Okay, so you kind of vary your policy according to that. If you've got an ace in your hand, of course you can afford to ask for more cards more often, because that ace can either be a 1 or 11. And then this is what the value function looks like. So it's just a continuation of that last example to show you that, you know, this process really does end up with usable information, in the sense of, you know, you get these nice shapes out of these value functions that really characterize exactly the optimal behavior in this domain, and you really end up with something which is the optimal policy. There's no way to do better than this in this particular game that we've described. This is the optimal way to behave. Okay?
Why would you ever stick at 11? Because you can't go bust.
You wouldn't. It always says to hit on 11.
When dealer is showing between 4 and 6.
So this line here says if you're on 11, you always hit. This
Sorry.
region here.
So the line is between 11 and 12.
So it's like a grid, and each cell of this grid is indicating what to do. So this could be shaded in if you like.
Yes, yeah.
And showing you for 11, you should always hit. But if you've got 12 and the dealer has a bad card, there's some chance the dealer might go bust, and so you should just stick on that 12 sometimes. Okay. So we're now going to move on to temporal difference learning methods. So just like the last lecture, we kind of split things between Monte Carlo learning, and then we moved on to TD learning, and then we saw that there was a spectrum in between these two things. We're going to follow the same process now, but with control methods rather than evaluation methods. We're really going to try and understand how can we actually gain efficiency by bootstrapping, by using the same tricks that we saw last time, and gain a lot of the efficiency. We want to basically use TD. Why? Because it can be lower variance, because it can be run online in continuing domains. Even if there's no termination, you can still run this. It can be run from incomplete sequences. And what we'll see actually in this lecture is that there's an additional benefit to using TD, which is when you use off-policy learning. It becomes particularly important to use TD. And so the natural idea, well, let's try the obvious thing, which is use the same generalized policy iteration strategy, but we know that to do model-free policy iteration, we need to use Q. We need to use Q so that we don't have to do any look ahead in our to do our greedy or epsilon greedy policy improvement. And the idea is basically to use now TD learning to estimate Q. So let's just slot in TD learning in place of Monte Carlo policy evaluation and continue to use epsilon greedy policy improvement. And that's immediately going to give us an algorithm that we can apply, which is probably the best known algorithm in reinforcement learning. And the only difference we're going to do is because TD can operate at this higher time scale. So TD learning is something where you don't need to wait until the end of the episode to update your value function. In fact, you can update your value function after just one step. That's one of the advantages. It's online. Like you'd see one step of data, you bootstrap, you update your value function immediately. And so again, if we follow this general principle of always using the freshest, most recent value function to pick your actions, what we're going to do is we're going to increase the frequency of our policy improvement to be every single time step we're going to improve our policy. Okay? So the general idea is called SARSA. So why is it called SARSA? Well, this diagram should illustrate it. We're basically starting off in some state action pair. That's this black dot, the decision node. We're basically choosing an action. We're going to randomly sample our policy. So we're going to see a reward R. We're going to end up in some new state S prime, and we're going to sample our policy again to generate A prime. So there's two steps of sampling. Sorry, we're not sampling our policy yet. So we start off with state here. We're asking a question about this state S and this particular action A. We're going to sample from the environment to see what reward we end up in and what state we end up in here. And then we sample our own policy at that next state. So we end up with SAR S prime A prime, or SARSA algorithm. Okay. So SARSA basically indicates a particular update pattern that we're going to use based on SARSA here. And so what do we do? Well, we're basically going to start with our Q values. We're going to move our Q value a little bit in the direction of our TD target, reward plus our discounted Q value of the next state, minus the Q value of where we started. So again, it's like I was in some state and I'm considering taking some action. And what I want to know is, if I actually take that action, look at the reward I got, and then the value of the next action which I would take, that gives me an estimate of the value of this policy, and I'm going to use that estimate to update the value of the state action pair I started in. Okay, that's the general idea. This comes from the Bellman equation for Q. We've seen this hopefully before, becoming familiar with these type of ideas. So that's a SARSA update. Okay? So now we're going to take these SARSA updates and we're going to plug them in to our generalized policy iteration framework. So every single time step, we're going to move up and down in this diagram. Every single time step. So each time we take a step, we're going to update our value function by applying one step of SARSA. So for the state and action that we were just in, we're only updating the value function for that one state action pair at that time step by applying this update. So I was in this state action pair, I ended up in some new state action pair. I'm going to do one update to my Q value for that single entry of my table. And now I've already changed my value function, right? Something's different. If I end up back in that state action pair again, which I might in some loopy environment, I want to make sure that I use the latest, most interesting, most up-to-date, best information that I've got from my policy evaluation. So every single time step, we're going to improve our policy as well by acting epsilon greedily with respect to the latest value function. So again, what does this mean in practice? It means that you're just storing Q in your memory. You've just got this big table of Q values for all states and all actions. And every step when you actually come to take an action, you just flip a coin, you look at your Q values, and if it comes up heads, then you look at your Q values and pick the best one. If it comes up tails, you explore randomly. So the policy is implicitly represented by your Q values. And every single step, we're going to evaluate the latest action I took and update my policy just for that one state action pair. Okay? So we've really got this very rapid process of evaluating by SARSA and improving the policy. let's try and get to know this a bit better. So what would an algorithm look like? So I think it's actually useful in this case to just maybe step through some pseudocode. It's really straightforward. So you can arbitrarily initialize this lookup table. Q is just a lookup table. In subsequent next lecture, actually, we'll see how to generalize beyond these naive lookup table representations. But for now, it's just a lookup table. Every state, every action has its own entry in this table. We initialize this arbitrarily, just say 0. Okay? And now we're just going to repeat. And every single step, this outer loop is just over episodes, but really, the inner loop is just every single step. We're going to take an action, observe the reward, observe the next state that we end up in. We're going to choose our action using our epsilon greedy policy. And we're just going to apply this Sasa update to that one step. So update a little bit in the direction of my TD target, the reward plus the discounted value of the next state action pair. And then repeat. So the next time we come round, we'll already have a different policy because we're acting epsilon greedily with respect to our Q values. If I end up back in that same state again, for example in a loop, I will already behave differently using the latest and freshest information stored in Q. Okay. Yeah, question?
S dash is chosen according to E epsilon greedy as well?
S dash is chosen by the environment. S dash is the next state. So state.
Sorry, A dash.
Yes. So A prime. So the question was, is A prime selected according to the same policy? So A prime is selected using your current policy, and then you basically remember that, and now when you come in, you remember what your last A prime was. That becomes your A at the next step. So you just kind of remember your last A prime, and that becomes your new A.
How does that affect the equation? That you're choosing that, there's no reward coming from that last stage, right? The reward, the R that you're using there is from the intermediary stage.
Yeah. So the question is, why does this even make sense as an update, I guess? And so let me try and give some intuition. And I think the right intuition to have comes from the Bellman equation. That really what we're trying to do, this is just a sample of the Bellman equation. Like this right-hand side that we're moving towards, this thing here, this target, is a sample of the Bellman equation. We're basically saying what we want to do is we want to consider an expectation over everything which happens in the environment over one step, which basically is the reward plus whatever state you end up in next. So that gives you your expectation of the environment. And then this. And now we want to know, well, what would happen under our own policy? We want to know what would happen under our own policy after that point. We want the expectation under our own policy from that state onwards. And that expectation under our own policy is precisely what we're trying to evaluate with Q. So that's why it has to be evaluated. We have to select actions using the policy that we're trying to evaluate. This is an on-policy algorithm, fundamentally on policy. We're selecting actions and we're evaluating that policy. So Sasa is an on-policy algorithm. Okay. So you should be wondering, well, does this work? And just like Glee Monte Carlo, this version of Sasa actually will converge to the optimal policy. And the only thing we require is, again, Glee policy. So again, you could choose your epsilon greedy with this decaying schedule. That would be a valid choice, just to make sure that you continue to explore everything and that you eventually end up greedy. But you also need to be careful about the step size that you use. So you have to make sure that your step size, if you really want convergence, you need to look at stochastic approximation theory, and you need to make sure that your step sizes basically follow these two conditions. And all this tells you is that the step sizes are sufficiently large that you can move your Q value as far as you want. So you might need to move your Q value from whatever your initial estimate was to some very, very large or very, very low value if you're wrong. And this thing basically tells you that eventually the changes to your Q values become smaller and smaller and smaller. The changes to your Q values have to vanish and become 0 eventually, otherwise you'll still have noise and jumping around in your policy. So that's just stochastic approximation theory. But really, when you do all that, if you do all the machinery correctly, this thing really converges. In practice, we don't worry about this, and we sometimes don't worry about this either. And Sasa typically works anyway. That's an empirical result. But this is the theory, okay? So let's have an example. So this example actually is doing precisely that. It's throwing out this theory and just using a fixed step size and a fixed exploration rate. Let's see what happens. So this is called a windy grid weld. We're just trying to wander around from this start point to this goal. We can take any of these King's move operations, so all the diagonal moves as well as northeast, southwest. And the only special thing about this grid weld is that every time we take a step, the wind pushes upwards and pushes the agent upwards some number of grid cells which are indicated by this number at the bottom of the column. So there's no wind over these first 3 columns, then you get pushed up 1 step when you move here, 2 steps when you move up here, 1 step here and 0 here. So the optimal behavior is basically, it has to take account of the fact you want to make as much progress as you can when there's no wind, and I think you end up kind of taking this route, we'll see on the next slide, something like that as the optimal behavior. You have to come back around to get back to the goal.
Would you want to just go down and then be blown up to the goal?
That's not optimal. If you try to go down, then what happens is you end up being blown up 1, blown up 1 again, blown up 1 again, blown up 2, and you end up overshooting the goal. Okay? So you can try to do that, but you don't hit the goal. So you're better to get pushed up against the ceiling, come back around from the ceiling after that point, and come back to the goal again.
But if you can go diagonally downwards, or
Yeah.
diagonally to the right, then those first 3 you can just go horizontally. The way you're blown up 1.
So maybe this is a version that just uses the standard moves then. I'll have to check that. I think this might just use standard moves, and that the wind blows you into a diagonal direction. You're right, that would be true in that case. So here is the diagram of the optimal policy. So this plot basically shows us what happens if we use the naive version of SARSA. So it's just something to show you that, this is the policy that it finds, which I claim is the optimal policy. You can check that offline. And this plot here basically shows the learning curve for running SARSA. And so this is exactly the algorithm we just looked at. And what this is showing is actually the number of time steps. So this axis here is literally time step by time step. And what we're looking at is how many episodes were actually completed in those number of time steps. So you can kind of see here that the first episode took 2,000 time steps to complete. It started off with no knowledge about how to do this, and so it's basically just doing a random walk, and that random walk is biased upwards, so it's not even as good as a random walk, so it takes a long time to actually stumble on the goal. But when it does, and this is really typical of reinforcement learning and these generalized policy iteration algorithms, when it does, the very next episode, it does much, much faster, and you get these exponential increases, because once it learns some knowledge, it can bootstrap from that knowledge and do better and better and better and better as it starts to learn things. So it immediately learns faster and starts to complete episodes at a much faster rate now, until up here you can essentially look at the gradient of this, and the gradient of this should tell you the path length which it's taking, which I think is like 14 or something, the ratio between this and this, which is the optimal policy. So most of the time it's behaving optimally, but this is still, because we're not decaying epsilon, it won't be completely optimal because it will still be throwing in the odd exploratory action. Okay? And that's why it's got this bobbly look to it. Okay, so now we're going to take the step that we took in the last class, which is we're going to consider the spectrum between Monte Carlo and TD learning algorithms. We're going to consider these eligibility traces and lambda variants of these algorithms to see if we can again get the best of both worlds, get the best of the unbiased behavior that you get from Monte Carlo, and also get the best, or at least control the bias, have a knob that controls the bias variance trade-off. And so the way we're going to do that is start off by considering these n-step returns again. And so what we're going to do is consider these returns now, which are basically the one-step return looks at 1 step of real reward and then our Q value after 1 step. But we could also use the 2-step return. We could have looked at 1 step of reward here, a 2nd step of reward here, and then look at our Q value after 2 steps. Or we could do that for any number of steps all the way down to infinity, which is essentially Monte Carlo, where we look at the reward after 1 step, reward after 2 steps, all the way until the end of the episode, and we never bootstrap from our value function. Okay, so that was the idea of these n-step returns. And so this Q return we can define in the following way. We can define the Q return to basically be the generalization of this to any n. And n-step Sarsa just does the obvious thing, where we say for each state action pair, what we're going to do is instead of updating towards the one-step estimate of our value function using Sarsa, we're going to use this n-step return as our target. So again, this means we're going to take our estimate of the value of taking action A in state S. We're going to update that a little bit in the direction of our n-step target. Okay, this is this sort of idea of the incremental mean, this non-stationary updates again. And this n-step target now is, essentially saying, well, I'm going to look at, 1, 2, 3 steps, and then bootstrap from my Q value, which represents the value of the remainder of the trajectory. I'm going to use that as my estimate of the overall value of the trajectory, and use that to update my value of the state I was in and the action I took from this starting point. And we can do this for any n. And so again, just like in the last lecture, we want to be able to consider algorithms which are robust to the choice of n, and which average over many different n's. We want algorithms which kind of get the best of all possible n. Yeah.
So I want to ask just for reminder. So the Q function represents like the estimate of the whole trajectory from ST in the using action A, right?
Yes.
Not the not trying to estimate only the one step.
Yeah, that's right. So all value functions. So let me be clear about that. So all value functions, including V and S, are long-term estimates of the amount of reward that you get. So the definition of Q is the expected total reward that you get if you start in state ST, and then you take action AT, and then you follow your policy for all subsequent actions.
Mm-hmm.
That's the definition of Q. So it specifically is a long-term estimate. We never consider just these, like even when we're talking about these n-step returns, that's just our target. It's still an estimate of the complete return, but we're estimating that by looking at n steps of immediate reward, plus something which summarizes the remainder all the way out to infinity or the end of the episode of the remaining reward, all discounted by the appropriate discount for each step. Okay? People good with that? Right. So, let's make a lambda version of this algorithm. So, this algorithm is called Sarsa lambda, very well-known algorithm. So what we're going to do is we're going to consider, first of all, just the update. Like, what does this look like before we talk about the full algorithm? And the idea is we're going to basically average over all of our n-step returns. So we're going to consider starting in this state action pair. The environment pushes me to this state. I take some action, and then I estimate my Q value here. And we're going to weight this particular return by 1 minus lambda. We're also going to say, well, what if I start in this state action pair? Environment picks a state, I pick an action. Environment picks a state, I pick an action. We're going to look at the Q value, add up the rewards along here, plus the Q value at the end of this, weight this by 1 minus lambda times lambda. So each time we're going to multiply by another factor of lambda. This 1 minus lambda is just like to normalize the whole sum to add up to 1. So we get this weighted sum of all of our n-step returns, where we basically are looking, we take more account of the trajectories which are of the shorter n, and then we progressively discount by another value of lambda as we increase n. So the main idea is to now make this average return. So we had this these returns which were n-step returns, and now we're going to average over all n. And the way we're going to average over them is just by defining this weighting, just like over here. We're going to weight each n-step return by a factor of lambda to the n minus 1. Just the normalizing factor there. And so when we make this lambda return, this is just a way to average over all of our n-step returns in some way that's A, computationally convenient, and B, takes account of all different n. Okay? And it has this lambda parameter that we can tweak, which can make us either more or less far-sighted in terms of how much we prefer the large n or the short n. Okay? And so this gives us, now we can plug this right into our update. And so again, what we can do is we can say, now I'm going to update my Q value. I start over here, and now I'm going to consider a weighted sum for this Q value. I want to know how good is it to take this action. And I'm going to consider some weighted sum that takes account of my estimate based on my Q value, my reward plus my Q value from here, but also based on my reward plus my reward again, plus my Q value from here onwards. We're going to weight all of these things together, all the way up to n equals infinity. That's going to give us our Q lambda, and we're going to make that our target, and we're going to update our original Q value a little bit in the direction of that target. Okay, so that's the idea of Sasa lambda. We'll see an illustration in 2 slides. Just before we do that, I want to spend 1 slide just saying that this was the forward view. If you remember from the last lecture, there was a forward view and a backward view of how to use TD lambda. That with these eligibility traces, we can actually come up with a back. So what's the problem with this approach so far? So this is great. We've got something which lets us build a spectrum between Monte Carlo algorithms and TD algorithms. So we've got now a variant of Sasa that can look all the way out to the future. If we set lambda to 1, it turns into Monte Carlo learning. If we set lambda to 0, it turns into our familiar Sasa that we saw in the previous steps. So now we've got this control where we can choose, our bias variance trade-off in between and average over all of these things. The only problem is that we're kind of looking forward in time. That this isn't an online algorithm. It's not something where we can take 1 step, update our Q value, and immediately improve our policy, because we have to wait until the end of the episode to be able to compute our Q lambda. And we'd like to be able to run things online and be able to get the freshest possible updates immediately, and have this kind of clock ticking over every step of getting the maximum amount of our policy improvement by making an adjustment every single step and running online. We don't want to have to wait until the end of the episode. There might not even be an end of the episode. This might go on forever. So what we're going to do is come up with an equivalent, just like in the last class, by building up eligibility traces such that when we sum up over those eligibility traces, we're going to end up with an update which is exactly equivalent to this one. And so the idea is very similar to the last class. We're going to build an eligibility trace now, but the eligibility trace is going to be for all state action pairs. So now we've got a new table, a table of our eligibility for each state action pair. Think of this as the thing which is telling you how much credit or blame you should assign to every action you took from every state. Like you end up, at the end of your episode, you get a big carrot at the end of your episode. So which of the states and actions are responsible for that carrot? And your eligibility trace is your best estimate of who was responsible for receiving that carrot. And so what we do again is we say that the states and actions that I took that were most recent before I got the carrot, and the states and actions that I took most frequently along the trajectory are the ones which should be blamed or credited the most for their negative or positive reward that I receive at the end of that trajectory. And so the way we do that then is we can do it online by just increasing this state action pair. So every time we actually visit a state action pair, so if we actually visit it, we increment it. So this is just something that says, this is an indicator saying if I'm actually in that state S and take that state, that action A, then I'm going to increase this eligibility trace by 1. Okay? So if I actually see that particular state action pair, increase my trace, and then every step for all state action pairs, even the ones we don't visit, we're going to decay them a little bit over time. We kind of have this process where, if I'm going round and this is the state that we're really considering here, and if I keep going round and every time I revisit this state, I'm going to bump up my eligibility, and over time it's going to decay until I get back there again, and then it's going to bump up again. And then if I receive my carrot, whatever the latest eligibility is, that's how much blame I'll put on that particular state. And so what do we do then? Well, now we've got these eligibility traces, we just update our Q values for every state and every action. We update in proportion to the TD error, that's the event that happens of getting the carrot, or the surprising event where you got more or less reward than you expected. And the credit or blame that you assign is proportional to your eligibility trace. So now the algorithm is to say, let's update our Q values in proportion to the TD error, the difference between what I thought was going to happen and what actually happened, multiplied by this credit assignment trace, this eligibility trace. Yeah, question?
Is there a way to apply this to very large state spaces where you don't effectively ever visit the same space twice, where you're using functional approximation for your value functions?
So the question is, can we do this in very large state spaces where you can't store this table? Next class. So next class we deal with function approximation. For all of the algorithms we've seen so far, we all generalize to function approximation in the next class. And so the answer is yes, you can do that and should do that, because
The traces.
table lookup is typically naive and you can't solve large problems until next class, and then you'll be able to. So Sarsa lambda, it looks something like this. So we're going to basically initialize our eligibility traces to 0 at the beginning of each episode. You want to say, well, I can't blame anything yet, I haven't seen anything. And then for each step of the episode, we take our actions using our policy. We're again on policy here. So we pick our action from our policy, for example, acting epsilon greedily. We compute our TD error, so we look at the difference between the reward plus the value of the state and action I ended up in, minus compared to my previous estimate. So this is just the one-step error between what I thought the value was going to be before and what I think the value is going to be now. We increment our eligibility trace. We decay all our eligibility traces down here. So here we're just incrementing the state action pair we actually visited, but here we're decaying it for all states and actions. And for all states and actions, not just the one that we visited now, we do an update, because we need to update everything in proportion to its eligibility, not just the thing which we visit at this step. Everything might be blamed now or credited for what happens. So we need to update all state action pairs. And we update them all in proportion to the TD error and the eligibility trace. And we just iterate every single step. So what does that look like? So I think this hopefully will help to get some flavor of what the difference is between Sarsa lambda and standard Sarsa. So imagine you're in some grid world where you're trying to get from here to this goal state. This could be like the windy grid world we just looked at. And you do some random walk to begin with, and eventually you end up there. Okay? And now let's say that you start off initializing all of your state action values to 0. Okay? And now what we're going to do is indicate the value of those state action pairs by an arrow in the direction of that state action pair, and the size of that arrow indicates how big our Q value is for that particular action. So what would the updates look like? Well, if you just did one-step Sarsa, you get to the end here, you started off thinking you had a value function of 0 everywhere, you get to the end and you're like, aha, I actually got a reward of 1 once I reached there. So surprise, now you need to make some updates to adjust the values of your trajectory towards what actually happened. But in Sarsa, if we look at the updates which are made at every step, at every other step apart from the final one, like here, we thought the value was 0. After this step, we also thought the value was 0, because we initialized all our Q values to 0. So nothing changes here. Over here, we thought the value of going right was 0. We ended up in a state where if you go right, you get a value of 0. So again, nothing changed here. The only place you get a change was in this very final step here, where you thought you were in a situation where if you go north, you got a value of 0, but then you ended up in a situation where you got your carrot. So now, this guy will be updated, and you'll end up adjusting this one to say, okay, now you're going to have a very nice positive increment. You're going to increase this value of this action going north to some higher value, and you'll think that this was a good action. Now if you run another trajectory, and you end up coming back through that same action, that will now propagate backwards one further step. So if you were over here now, you start in this situation where you thought the value of going left was 0. You ended up in a value where you're now estimating the value of going north to be something high. So now you would increase the value of this guy, for the value of going west from here, you would increase by some large amount. At the next step, that would propagate backwards. At the next episode, it propagate backwards again. But you need a lot of episodes. You're only propagating the information back by one step per episode in Sarsa 0. Okay? In Sarsa lambda, it looks quite different. So the lambda parameter determines how quickly, how far that information should propagate back through your trajectory. So again, if we consider the same trajectory, you would build up your eligibility all the way along this trajectory. So each of these state action pairs that you visit would have their eligibility trace increased. The the first ones would have decayed quite a bit, down towards 0. The ones more recent would have decayed less. And now when you actually see this reward of 1 at the end, you would increase all of those state action pairs in proportion to your eligibility trace. So that means all of them, when you see this surprising positive benefit, all of them get updated in the direction of what actually happened. So this information flows backwards in just one episode, most of the way back towards the beginning of the episode. So you get a much faster flow of information backwards through time by choosing this lambda parameter. So the idea of lambda is it, so we can say that it basically defeats the tyranny of the time step. That if you have many, many, many time steps, SARSA 0 is always susceptible to the fact that you need more and more steps to actually flow this information back. Whereas using a lambda parameter, you can always just pick your lambda so that information flows back at the right rate, regardless of the granularity that you make your time steps operate at. So lambda basically overcomes this tyranny of the time step. Okay, any questions there before we move on to the final section? Yeah.
You said that the eligibility traces would decay along the path, but
Yes.
it's going to be 1,
No, or so if we go back to the updates in the algorithm, the eligibility trace is incremented in all the states and actions you visit, but it's also decayed every time step. It's decayed by a factor of lambda, and also by your discount factor gamma. So that's why this lambda parameter sets the rate at which how far back in time you look, because now you've got this decay rate, which basically tells you how steeply you want your eligibility trace to decay going back along this trajectory. So if you set lambda to 1, these will be of equal magnitude, like these arrows would still be thick, like the updates that you make all the way along the trajectory would still be large, and that's what happens in Monte Carlo, because in Monte Carlo, you run your trajectory, you see that you get some eventual reward, and everyone gets updated in the direction of that reward, because everyone says, hey, I took this action, I ended up getting something good, I should be updated. So by tuning your lambda, you basically determine how far back along this trajectory you look. It controls your bias variance trade-off. The further back you look, the more variance you have, because there are all these random things which happen along this trajectory. But you reduce your bias. You're less susceptible to the effects of bootstrapping. Okay. Question at the back. Yes.
Yeah, I thought you said that for the backward you don't necessarily need to wait until the end of the episode, but here you can do that.
You don't need. So okay, the great question. So the question was, why wait until? So for the backward view, the advantage is supposed to be you don't need to wait until the end of the episode. So we're actually running an update every single step. Now the fact that the reward only occurs at the end of the episode means that you don't actually gain any information until you reach there. So these arrows are basically showing you, by the time you get to the end of the episode, what's the effective update that you see. But the nice thing about, imagine that you pass through this reward and then you carry on, and then you get another reward, and then you get another reward, and then you get another reward. So what would happen with SARSA lambda is that nothing would happen until you hit your first reward, and then immediately all of these guys would be updated, even though you haven't finished your episode. You would carry on and you would carry on and you would carry on until you hit your next informative event. Then everything would be updated because of that next informative event, and you would carry on and you'd carry on. So the fact that nothing happens isn't because we had to wait until the end, it's because actually that we gained no information until this point. Like until this point we thought the value was 0 everywhere, and we got 0. So we are making updates at every single step, it's just those updates contain 0 information until the first informative event. But you're right, I think this example, it's not clear from this example that is really a property of the online algorithm. Okay, there was one more question.
Yeah, so these are the action values, and over many episodes we're basically going to be taking immediately, so I just want to clarify that.
So in SARSA we never take an explicit mean, we just use these SARSA updates.
Yeah.
So the updates that we do are precisely the updates that we saw in the algorithm, which are basically updating the Q values a little bit in the direction of so if we see some reward where we thought there wasn't going to be a reward, that generates an error. and we update every value a little bit in the direction of these, of our TD error multiplied, our unexpected reward that we got, multiplied by the trace, by the credit that we're assigning to each of those states and actions. That's it. That is the process by which we estimate the mean. So there's no additional step of taking the mean. It's an incremental way to estimate the mean value, if you like, the expected value. But we're not forming explicit mean, and furthermore, we're forming this non-stationary estimate. And actually, that's a point I should make more explicitly, which is if we look at the updates that we make. So we use this fixed step size alpha. So could you just take the mean by using, say, a 1 over n? Like, could we do the same thing that we did in Monte Carlo, where you count the number of times you visited that state action pair and plug in 1 over n as your step size? That would give you like a mean, an incremental way to estimate the mean. But the thing which you're plugging into that mean is changing all the time because you're bootstrapping. So it's not really the same as forming a true mean. You're forming like a non-stationary mean of that. You're throwing in there all of these different targets that you've seen at all these different times. So I think the right answer to your question is that we are forming an estimate of the expected reward, the expected future reward, all the way to the end of the episode. One way to estimate that is using Monte Carlo learning, which explicitly estimates the mean. Another mechanism for estimating that expectation is by bootstrapping. And that's sort of, instead of computing the mean, we now update a little bit in the direction of the errors that we see. So we bootstrap, we look at the error, and we use that error to inform what we think the previous value should have been. And that is the process by which we estimate the expectation. Okay. And again, the equivalence between the backward and forward is not obvious, but it is possible to prove. There was a proof in the last lecture, and that proof follows through for the control case as well, roughly. But I think a useful way to understand what's going on is to understand that really what we're doing when we do these traces is to implement this algorithm here. So we're implementing an algorithm in an incremental way, which is basically updating our Q values a little bit in the direction that mixes over our estimates at all these different time scales, where we bootstrap from n steps, from all different n step returns. So you start in some state action pair. So if we go back to this view here, another way to look at this, what would the forward view look like? So forget eligibility traces. The forward view would say, you start at each point in this diagram. Now you really do wait until the end of the episode. That's the forward view. At the end of the episode, from each of these states, we would consider the one-step return, which will give you no information. We'd consider the two-step return, which will give you no information. Consider the three-step return, which will give you no information. And the only one which will give you the information is the longer returns that go all the way to here or beyond. Okay? And the amount that you take account of those things, the weights that we put on that final n, on that largest n, the weight that we put on our final one, is precisely the amount by which we would update that guy here. And so if you're very close to the end here, all of your weight goes on your return, on your final return, because the episode stopped here. Whereas if you're way back at the beginning here, a lot of your weight is going on these shorter returns that don't contain any information yet. And so that gives you the same effective result. You can see just intuitively that just looking at these diagrams, you get the same picture by either this forward view computation or the backward view computation. But the backward view is computationally much nicer. We do that online. You just keep one step in memory. You just do that thing. You move on. You don't need to look forward in time or wait until the end of your episodes. It works in situations where you don't even have episodes.
Can I just ask one quick question about the size of it's just storing the eligibility trace in a computer. So is that a kind of matrix which has got two dimensions? One is the number of states, and the other dimension is the number of actions.
Yes.
So
in this lecture, we're building tables for both Q, which is a matrix, number of states times number of actions, and eligibility trace, and the count when we were doing Monte Carlo, this n x comma a. All of these quantities were tables, and the tables were number of states times number of actions in size. You can store that as a matrix, if that's a helpful way to think of it. In the next class, we're going to look at ways to approximate that potentially very large matrix by an arbitrary function approximator with a smaller number of parameters for both Q and also for eligibility traces. Okay, let's change gear a bit. Now we're going to talk about off-policy learning. So everything so far has considered the case of on-policy learning, where the policy which I'm following is the policy that I'm learning about. But there are many cases where we want to consider how to evaluate some other policy while we're following. So let's say we're going to follow some behavior policy that we're going to call mu. So this is the behavior policy that we actually pick actions from in the environment. So mu. And what we want to do is to evaluate some other policy, pi, so as to compute, say, v pi or q pi, or ultimately figure out maybe the optimal way to behave in that environment. But the behavior that we see is not going to be drawn from this thing that we're wondering about. So why would we want to do that? Why do we care about off-policy learning? So here's 4 possible reasons that you might care about this a lot. Okay. The first reason is that you might want to learn from observation of other agents, like humans. You might want to see how humans behave, and not just do supervised learning to copy what the human did, but look at the traces of behavior, look at the episodes of behavior that the human executed, and actually, just from that experience, figure out how to do better, figure out how to solve the MDP just from watching some human, steer some boat around, and then look at what they did and say, I know how you could have done better. You could actually have got more reward by following this other path around. That's the goal. Okay, we want to be able to observe some other policy and maybe figure out how to do better, or learn from that behavior, learn from one behavior what the value of another behavior would be. A specific case, we use this, for example, in the Atari work that I mentioned in the first lecture, is to reuse experience from old policies. So this is a case where, imagine now that we're doing our generalized policy iteration. So we move through a whole sequence of policies when we do that. We start with some initial random policy pi 1, and then we make it a little bit better to give us pi 2. Eventually we end up getting better and better policies. But what if we want to go back over the data that was generated using those old policies and use it more than once instead of just discarding this data, which is very data inefficient? What if we want to go back over it and look again and say, oh, I remember I did this thing, I've seen this state before, when I was last here I did this other action and I got this other reward. Reuse that data, do something a bit more like batch methods, where you kind of you just treat this as a big data set and figure out how to do the best thing from that data set. Well, what's the problem there? The problem is that we're trying to evaluate our current policy. And when we're doing policy iteration, we want to know, this is our current policy, we want to know how good that is. But we've generated behavior using all kinds of different policies. So is it possible to make use of this additional data to get a better estimate of the value of this final policy? And the answer is yes, if you use off-policy learning. You can basically just treat this as other behaviors that generated that data, just like the human. This could be, think of this as the human, and this is some other robot, and you kind of just want to look at all of that data and figure out from all those other sources of experience how to do better. Probably the best known example of where off-policy learning is used is this third point, which is to say, we know that there's this big issue in reinforcement learning, which is making sure that you explore the state space effectively. At the same time, we want to learn about the optimal behavior, which doesn't explore at all. So why not make use of off-policy learning to generate, now we can have an arbitrary exploratory policy that just explores around with as much exploration as we want, and at the same time learn about the optimal policy. That requires us to be off-policy. We want to learn about how to behave optimally, something which is ultimately going to be deterministic, whilst following something completely random. Okay? That's another motivation for off-policy learning. And perhaps looking forward, to grander visions, the most exciting reason to care about off-policy learning is we might want to learn about multiple policies while following one. So there might be many different behaviors we want to figure out. I might want to know, what will happen if I leave this room? How much reward will I get? Will you guys be pleased or disappointed? I don't know. Maybe I should figure that out whilst carrying on talking to you. But I might also be wondering what would happen if I changed the topic and went back to 3 slides ago. There's all kinds of questions I might be asking about the future, which are conditioned on following different policies. And I want to know what would happen if I followed all of those policies, and I want to learn about them all from one stream. I only get this one stream of data that we call life, and I want to learn about all of these other policies and figure out the answer to all kinds of different conditional questions whilst following that one stream of experience. Okay, these are all reasons to care about off-policy learning. So it's a significant problem, and it's actually a thorny problem for reinforcement learning, as we'll see next class. But we're going to look at two mechanisms for dealing with this. The first of which is importance sampling. Oh, I used a lot of time advertising it, so let me talk about this. So the first mechanism is to basically do importance sampling, and the main idea there is to take this expectation. There's some expectation, like your expected future award, and all we do with importance sampling is to say an expectation over your, say, your future award is just to sum over some probabilities times, say, how much reward you got. And now what we can do is just multiply and divide by some other distribution. And now this ratio here that we've got, you can basically say this is an expectation over our other distribution of this quantity here, where all we had to do was kind of divide out our old probability. And basically you multiply and divide by the ratio between your old and your new distributions. And that corrects for the change between your distributions. So we can apply importance sampling to Monte Carlo learning by basically doing importance sampling along the entire trajectory. So when we importance sample in Monte Carlo, we have to look at the trajectory. We have to multiply these importance sampling ratios across the entire trajectory. Like every single step, there was some action I took according to my behavior policy, and there's some probability that action would have been taken under the behavior I'm actually trying to learn about. And so it kind of, you have to multiply these ratios together, and in general it becomes a vanishingly small probability that the return that you saw under your behavior policy actually matched, gives you any information at all about what would have happened if you followed some completely different behavior. So you can use this idea, but it's extremely high variance, and in practice it's just useless. Okay? So Monte Carlo learning is a really bad idea off policy. It just doesn't work because over many steps your target policy and your behavior policy just never match enough for it to be useful. And so you have to use TD learning when you're working off policy. It becomes imperative to bootstrap. And so the simplest idea to use TD learning is just to importance sample, but you only need to importance sample over one step now, because we're bootstrapping after one step. So all you have to do is basically update your value function a little bit in the direction of your TD target. And the TD target now, all we're going to do is take that TD target, like what happened over one step of this action, we're just going to correct for our distribution over that one step now. We're going to say, over that one step, I had some behavior policy that generated some action, and there's some probability that I would have taken that same action under my actual target policy I'm trying to learn about. And we just consider the ratio between those two things, and we multiply our target by those things. So that we weight how much we trust this target that we look at by how much our policy really matched what was actually taken in the environment. If these don't match at all, we can't consider this. Essentially, this basically leads us to infinitesimally reject something or to take huge account of something. So you can still get high variance. We still increase the variance by importance sampling, and it can still blow up, but it's much, much better than Monte Carlo. Now, the idea which works best with off-policy learning is known as Q-learning. This is specific to TD0 now, to SARSA 0, for example. And what we're going to do is consider a specific case where we're going to make use of our Q values. We're going to make use of the action values to help us do off-policy learning in a particularly efficient way that doesn't require importance sampling. And so the idea is very simple. The idea is we're going to select our next action using our behavior policy. Okay? But we're also going to consider some alternative successor action that we might have taken had we been following up our target policy. So we sample, this is our random variable representing the real thing we took in the world, that's time step t plus 1. And this a prime is like our alternate thing, like we're just imagining if I'd taken this thing under my target policy, you know, what might the world have looked like. And now all we're going to do is we're going to update our Q value for the state we started in and the action that we actually took. We're going to say, well, the value of that state and that action that we actually took, we're going to update towards the value of our alternate action. So when we bootstrap from the value of our alternative action, because that's the thing that tells us how much value we'd actually have got under our target policy. Like when we sample from from this guy, that tells you something about what really would have happened under our target policy. So it looks a bit like this. We now replace our SARSA update, where we have our Q value for S and A being updated a little bit in the direction of the reward that I actually saw. So I was in this state, I took this action for real, even though it wasn't the one that I would do now. It doesn't matter, we're just asking how much value would I get if I took that action. I'm going to update it a little bit in the direction of the reward plus the discounted value of the next state of my alternate action under my target policy. This is what would have happened if I was really following the policy I care about. So this is a valid update. This is the Bellman equation again. It's completely valid. The Bellman equation for Q doesn't require us to importance sample. We're sampling that kind of Bellman equation. That's the idea of Q learning. Yeah.
Can you just be clear, like, which parts are from your behavior that you stored and which is online in that last equation? I don't know.
Nothing is stored. I'm not sure. So, well, the Q
so
values
you're
are
sampling
stored.
AT plus 1 from...
So you're sampling AT plus 1 from your behavior policy, and you're sampling A prime from your target policy. So each time you get to a state, you're considering the thing you actually took, and you're also, that's generating your real behavior, the thing you actually took, and that's the trajectory you're actually following. But at every step, you're also considering some alternate action you might have taken, and that's the thing that you bootstrap from. You bootstrap from that Q value. Now there's a special case of this, which is the well-known Q-learning algorithm. So if you hear about the Q-learning algorithm, essentially is what we're going to talk about in this slide. And it's a special case where the target policy is a greedy policy. So this is the special case where we're trying to learn about greedy behavior while we're following some exploratory behavior. And the special thing about Q-learning is that both the behavior and the target policies can improve. We allow improvement steps to both of them. But what we're going to do is basically at every step, we're going to make the target policy greedy with respect to our value function. So we're going to ask about this deterministic thing, which really acts, you know, as aggressive as possible. We're trying to learn aggressively about what we consider to be the best behavior given our Q values. But our behavior policy is going to be epsilon greedily. So our behavior policy is roughly going to follow sensible things to get us to good parts of the state space, but it's going to explore a little bit as well to make sure we get to new things as well. And when we plug this in to the previous slide, we basically end up seeing that, so this is the target that we had in the last slide, our R plus Q, the Q value of our alternate action. Our alternate action is this argmax, the greedy policy. So when we plug in this argmax, if you basically want to know what's the Q value of the argmax of your Q values, that's the same as the max of your Q values. So it's basically what Q-learning does is it updates a little bit in the direction of the maximum Q value that you could take. So that looks like this. So we're just going to have one diagram to display this. This is the well-known Q-learning algorithm. I call these SARSA max updates, because you're looking at S, A, R, S prime, and then the max over your A primes. And what we're doing is we're maxing over these guys. We're updating our Q values a little bit in the direction of the best possible next Q value you could have after one step. That's the idea. So it should be familiar from the Bellman optimality equation. This is basically just like the Bellman optimality equation. And this algorithm, again, converges to the optimal action value function. And so it's a standard idea for reinforcement learning. So just to wrap up, I just want to bring out these relationships between these full width updates that we had in dynamic programming and what goes on in temporal difference learning. So in this column here, what we've got is a dynamic programming algorithm that we looked at in the previous lecture. On the right-hand column are these sample-based algorithms, TD and algorithms that we've looked at in the last lecture and this one. Okay, and so if you use the Bellman expectation equation, so this is which Bellman equation you use. If you use the Bellman expectation equation for the value function v, for the state value function, you can use dynamic programming to evaluate your current policy, or you can just sample this thing and take just one sample of this diagram by sampling from the environment and sampling from your policy, and that gave us TD learning. So these guys are just a sample of these guys. Wherever you've got an expectation here, you sample it to get your TD learning algorithm here, and that gives you your target. So the target for your TD learning algorithms are samples of the right-hand side of the Bellman equation. When we do the Bellman equation for Q pi, we can actually do SASA now. So when we use the Bellman equation, the Bellman expectation equation for Q pi, we can use that to evaluate our Q values and then plug that into our generalized policy iteration to make our policies better and better and better. So we can either do that using a policy iteration framework for dynamic programming, or that gave us the SASA algorithm. And then finally, we can use the Bellman optimality equation for Q star. And when you use the Bellman optimality equation, you can either plug that into value iteration, which is the dynamic programming method, or you can just sample this, sample your expectations to give you the Q learning algorithm. Okay, so TD we can think of as samples of the Bellman expectation equations, or the Bellman optimality equations. They're kind of doing a one-step sample of what would happen if you were doing dynamic programming. So that's just kind of to tie things together. Okay, thanks everyone. Next week we'll talk about function approximation, how to scale up, how to make these things work in larger and more practical examples. Cheers guys.